Humanity has always gazed at the stars with a sense of wonder. The vastness of the universe has always sparked our curiosity and imagination. For centuries, the speed of light seemed an insurmountable barrier. It was a cosmic speed limit that no object could surpass. However, in 1994, physicist Miguel Alcubierre proposed a radical idea, a warp drive. This concept was revolutionary, suggesting that faster-than-light travel might be possible. This concept, grounded in Einstein's theory of general relativity, offered a glimmer of hope for faster-than-light travel. By bending space-time itself, a spacecraft could theoretically move faster than light without violating the laws of physics. The idea of traversing the cosmos at speeds exceeding that of light has captivated science fiction enthusiasts for decades. From Star Trek to countless other sci-fi narratives, warp drives have been a staple of our futuristic dreams. Alcubierre's work suggested that perhaps these seemingly impossible engines could be more than just a figment of our imagination. His theoretical framework provided a scientific basis for what was once purely speculative fiction. His paper, published in the journal Classical and Quantum Gravity, ignited excitement and skepticism within the scientific community. It opened up new avenues of research and debate about the feasibility of such technology. While the mathematics of Alcubierre's warp drive hold up to scrutiny, the practical challenges of actually building one are immense. The energy requirements alone are astronomical and the engineering hurdles are daunting. Yet the allure of warp drives continues to inspire scientists and dreamers alike, pushing the boundaries of what we believe is possible. In the world of theoretical physics, the year 1994 stands out as a pivotal moment. It was a time when the boundaries of our understanding of the universe were being pushed further than ever before. This was the year when a young PhD student named Miguel Alcubierre published a groundbreaking paper that would forever change the way we think about space travel. Alcubierre's paper introduced the concept of a warp drive, a theoretical propulsion system that could enable faster-than-light travel. His idea was revolutionary, suggesting that by manipulating the very fabric of space-time, it might be possible to achieve what was once thought to be purely science fiction. He proposed that by creating a warp bubble around a spacecraft, one could compress the space in front of the vessel and expand the space behind it. This would effectively allow the spacecraft to move faster than the speed of light without actually breaking the cosmic speed limit. The foundation for Alcubierre's concept was laid by none other than Albert Einstein. Einstein's theory of general relativity had already revolutionized our understanding of gravity and space-time, showing that massive objects could warp the fabric of the universe. Alcubierre took this idea a step further. He suggested that if we could manipulate this curvature in a controlled manner, we could create a warp bubble around a spacecraft. This bubble would allow the spacecraft to travel vast distances in a fraction of the time it would normally take. Imagine a surfer riding a wave. The spacecraft inside a warp bubble wouldn't be exceeding the speed of light locally. Instead, it would be carried along by the wave of space-time itself, much like a surfer rides the crest of an ocean wave. The bubble itself would move through space-time, compressing the space in front and expanding the space behind. This ingenious method would allow the spacecraft to effectively surf through the cosmos, bypassing the limitations imposed by the speed of light. This would allow the bubble and the spacecraft within it to travel vast distances in a shorter amount of time. The implications of Alcubierre's work are profound, opening up the possibility of interstellar travel and the exploration of distant galaxies. The Alcubierre warp drive relies on manipulating space-time itself. Picture a flat sheet of rubber representing space-time. Placing a heavy object on the sheet causes a dip, illustrating gravity. Now, imagine folding the sheet, bringing two distant points closer together. This folding of space-time is what the Alcubierre drive aims to achieve. The warp bubble, a region of distorted space-time surrounding the spacecraft, is key to this process. Within the bubble, space-time remains relatively flat, meaning the spacecraft wouldn't experience adverse effects like time dilation. However, creating this warp bubble requires a form of matter with a negative mass. The concept of negative mass is one of the most perplexing in physics. While we're familiar with positive mass, negative mass behaves counterintuitively. Imagine pushing on a box filled with negative mass. It would accelerate towards you. This bizarre behavior arises from negative inertia. Negative mass has never been observed in nature, but its existence is not prohibited by physics. Some physicists believe it might be possible to create tiny amounts of negative mass using exotic quantum effects. However, the amount required to create a warp bubble large enough for a spacecraft is staggering. Initial calculations suggested a warp bubble would require negative mass equivalent to the mass of the entire observable universe. The quest to understand warp drives leads us to the unification of general relativity and quantum mechanics. These two pillars of modern physics seem incompatible when describing the universe at its most fundamental level. General relativity, formulated by Einstein, governs gravity on large scales, such as stars, galaxies, and the fabric of space-time itself. On the other hand, quantum mechanics, which emerged from the work of pioneers like Heisenberg and Schrödinger, describes interactions at the atomic and subatomic levels. When we try to apply both theories simultaneously, such as in the extreme conditions found at a black hole's singularity, the equations break down, leading to inconsistencies and paradoxes. This breakdown suggests that our current understanding is incomplete and a new theory is needed to bridge the gap. Quantum gravity represents our best hope of unifying these theories into a single framework. Quantum gravity aims to describe gravity according to the principles of quantum mechanics, providing a coherent description of the universe at all scales. Despite decades of research, a complete theory of quantum gravity remains elusive. Without a unified theory, we can't say for certain whether the space-time distortions required for a warp bubble would be stable. Would quantum effects cause the bubble to collapse? These questions remain unanswered. The search for this missing piece continues as scientists explore new ideas and conduct experiments to uncover the fundamental nature of reality. Only time will tell if we can unlock the secrets of the universe and make warp drives a reality. Until then, the dream of faster-than-light travel remains just that, a dream tantalizingly out of reach, but ever inspiring our quest for knowledge and discovery. The 30 years since Alcubierre's paper have been a whirlwind of research and debate. Physicists haven't given up on the dream of faster-than-light travel. They've explored new avenues of research and refined our understanding of the underlying physics. One major focus has been reducing the energy requirements of a warp drive. Early calculations suggested creating a warp bubble would require the energy output of entire stars. More recent research shows that by shaping the warp bubble, it might be possible to reduce these energy requirements. Some physicists propose using a ring-shaped warp bubble instead of a spherical one. This shape could potentially lower the energy requirements to something more manageable. One promising avenue of research focuses on the shape of the warp bubble. Early conceptions envisioned a spherical bubble, but this shape requires immense negative mass. Researchers explored alternative shapes to achieve space-time warping with less exotic matter. One such shape is the ring or torus configuration. In this model, the warp bubble resembles a donut with the spacecraft in the center. The negative mass is concentrated in the ring, creating compressed space-time ahead and expanded space-time behind. This configuration could reduce the negative mass requirement by several orders of magnitude. Other shapes, like elongated ellipsoids or warp pancakes, have been proposed. The key is to find a shape that minimizes negative mass while creating a stable warp bubble. Despite decades of research, warp drives remain theoretical. The challenges, from the need for negative mass to quantum gravity uncertainties, are formidable. However, the pursuit of faster-than-light travel has yielded invaluable insights into space-time and gravity. Current research focuses on refining our theoretical understanding and exploring new warp bubble configurations. Advances in quantum computing and experimental techniques are pushing the boundaries of our knowledge. While a practical warp drive might still be centuries away, the exploration has revolutionized our understanding of the cosmos. The quest for warp drive is a quest to understand the very fabric of reality. The dream of breaking the light barrier has captivated humanity for generations. While the technology remains elusive, the pursuit of warp drives has opened up a universe of possibilities. The journey towards faster-than-light travel is fraught with challenges, but it is compelling. Each theoretical breakthrough brings us closer to unlocking the secrets of the universe. The quest for warp drive is a quest for knowledge and understanding, and while the ultimate destination may be far off, the journey itself is extraordinary.
So hit that subscribe button, ring the bell for notifications, and let's turn the page on a new adventure together. Get ready to experience books like never before, only on VBook 360. Like, comment, and share to support the channel and keep the video magic alive. Thank you for stopping by. And remember, every video has a story, and every story deserves to be shared. See you in the next video.